Okay, so please sit down. We are going to start the session in a minute. I think we can start. Okay, so this is the last session of the day, and this has been a really productive day. We have been listening to some amazing talks. We started with the results from Sajay, and then we have these 4 wonderful invited talks. And so we heard first from Frank about the amazing results from the LTI. Congratulations! This is truly amazing what you can do with the LTI and infrared interferometer. We saw all the beautiful constraints on the orbits around Sajay, and I particularly loved the slide you have, Frank, with the image of the ngEHT of Sajay and the blobs that you have tracked previously. So and then too, we heard also about the importance of super resolution, and I think it was an honor to have here Jim Moran to tell us that we have to be careful. We need to put constraints in our imaging if we want to go above the nominal resolution of an interferometer. And then the beautiful talks from Sera and from Priya. I think you both touched on the relevance of multi-wavelength coverage. I think this is something that we have been discussing during the ngEHT working groups, that nowadays it's really important to have the multi-wavelength perspective, and also in this case also to have gravitational wave counterparts, and how relevant this may be for binary supermassive binary black holes, and to understand the results that we will get in the future from pulsar timing arrays as well as space interferometer. And so Priya also touched the relevance of having a population of black holes. So now we have 2 images. We have the images of M87 and Psi-J, but we want to do some statistics. We want to know how these supermassive binary black holes evolved and getting the spin, something that Frank was telling us that they are also trying to get. This is really relevant for constraining the history of mergers and how this supermassive black hole formed. So this is set at the stage for the discussion now. The idea is that we have our panel here, and this could be the open discussion about ideas and things that you may want to discuss a little bit with the panel and in general with the public. And I would say that we could start with very general ideas like what do you think will be the most relevant science that we should pursue in the next year in the study of supermassive binary black holes? What excites you more in the work ahead in the next 10 years, especially with improvements in the infrared interferometry and the ngEHT and ngEHT, what we have seen in this previous session, the amazing kind of science that we will be doing. So what is the thing that excites you more? So anyone from the panel, please. Go ahead, Jim.
It's really amazing what putting 2 and 2 together gets you 4, hopefully. But I was really my socks were knocked off by Frank's showing the picture, just showing the image of our torus in Sagittarius star with the orbital motion around it. I mean, I don't know why I didn't think of making that slide, but that really suggests that we ought to be coordinating the gravity observations in the future with the ngEHT. Of course, that's a 30-minute orbit. So we have to have the movie capability, but that would seem to be a very strong constraint, as it were, on our imaging. So I thought that was quite exciting.
I gotta say, we do try to coordinate with gravity, right? But it's difficult because VLT has very specific, VLTI specific times, and they don't always line up with ours. So if EHT can move into having a more agile observing, that's more flexible, like in July, where you're often doing your campaigns, that would work better for us.
Okay, we have also from the audience, Thomas, please.
Well, first, I do agree, of course, that coordination is very interesting. Maybe too naive, but I have difficulties in understanding why the size which gravity finds from the orbiting hotspot is almost a factor of 2 larger than what we see with the EHT. Normally, if you go higher in frequency, you penetrate deeper inside an optically thin or partially opaque atmosphere, and you would expect that the near-infrared is smaller than the radio. And now we are seeing something opposite. That means we are probably looking at quite different things. And we have also upper limits in the spectrum in the near infrared, also some real measurements, which indicates that the spectral turnover is perhaps above 230 gigahertz. So I wonder if there are any ideas to reconcile this in terms of a unified picture. Are we seeing dust in the near infrared, and are we seeing synchrotron radiation in the radio? Maybe somebody can clarify that.
So we see synchrotron also in the near infrared, actually all the way up to the X-ray. But what is different in what we see is we see that the electrons are not in the same temperatures where you trace it, but we see electrons at gammas of 10,000. So we are probably accelerated either in magnetic reconnections or in shock fronts. And so this happens then empirically farther outside. So we are not exactly on the last stable orbit, but there's a correct behavior outside.
Yeah. Could it be
also infer very strong magnetic fields, right? And these things much stronger and closer in.
We infer about 30 hours, which is a factor 7 after the quiescent, what we would call the quiescent state. And so this is what we indicate. So this is this kind of reconnection event, which actually really compress the magnetic field. Whether this is an MHD compression or whether there is more to get, I'm probably not the competent person to ask it, but our colleagues here. But indeed, it's a problem to still bring the microphysics to the MHD or vice versa.
I think I don't see it very well, but I think it's Jeff Crew.
Yeah, I just quickly wanted to comment on the challenge of getting a large number of facilities, an ever-growing number of facilities, all coordinated. Even at the existing array, getting everybody to the dance at the same time is getting ever more difficult with each station we add. And to be honest, unless you can get, I think a better approach is just to build the science case for more community support for this kind of stuff to overall get more time. And nature's serendipity is very likely to hand us what we're looking for, if we just do it often enough. I spent quite a number of years chasing gamma ray bursts, and there was one event that broke the thing open, and we had, half a dozen near misses prior to that. And, unless you've got unlimited funds, which we might get, but unless you have unlimited funds, getting that coordination is very difficult, and it's better to go for serendipity.
Can I just address that though? I mean, I agree with you 100%, which is exactly why the argument is that you just have to do this regular cadence. But on the other hand, I think with EHT, we've been unbelievably lucky when it comes to the Sagittarius coordination and some of the other things. I mean, we managed to catch flares at the same time as EHT 3 years in a row, which is very, we just guess when we put the x-rays on and then, manage to see this at the same time. So I think somehow it's working out better than we would have even have anticipated.
Well, that's right. But the thing that scared me about the cadence word is that, the reality is it's very difficult to guarantee everybody shows up, every 3 days. And okay, if you're not every 3 days, but on a variable cycle, you still are collecting the data and you can still do those variability studies and still learn a lot. And that one is what you're more likely to achieve than the radial. If we aim for a regular cadence, I just don't see how that's ever going to happen.
Okay. Can I make a couple of comments? So first, I think Jeff's comments are really good. The way we envision it with the ngEHT is that there'll be enough dishes so that you can lose, let's say 20% of your dishes due to weather or a technical issue, God forbid, and still have enough to make a good frame in your movie. So having more dishes in the same way that observing more helps you, just gives you a lot more contingency. So this is a case where more is a lot better, right? Because you don't need all the dishes to make one frame in your movie. And I want to tie it back because Jim's point is really interesting. But I'm wondering, Frank, if there's one model that gives you the EHT image at submillimeter or millimeter and gives you the orbiting, highly polarized gravity material, because it has to be part of the same thing, unless it's completely disjoint, as Thomas was saying. And so I want your comment on that. And then moving down this way, do we need to think about panchromatic multi wavelength observing for all of those cadences? Like, in other words, for every frame of the M87 movie, do we also need the full multi-wavelength campaigns? Because that's going to be tricky. Sorry, that was a lot of questions. Maybe first, Frank.
Well, many thoughts in what you said. For me, it's not so clear actually whether we can so easily link what you observe with what you observe in the infrared. Certainly on the very short time scales, even from the technical side, so with the limited UV coverage, see, this was what Jim was bringing. The SNR for us makes the difference to resolve or not resolve, but to trace, because the model at a given time is so simple that for us it's dominated probably by a single point source, which is not the emission which you see in your image. And then whether actually the development of your image and our image actually, we also don't know yet how this energy, if it's released in a reconnection, is actually then spread and propagated into the region which you have. So it's still a subject of what is in debate, I would say. There are different opinions how this goes. The empirical evidence is not conclusive. I would say there are different pictures in there. For me, this multi-wavelength is much we try. It's hard. It's a difficult one because it's so expensive. I don't know. Can I check the other thought and then I hand over? So Jim, or to you, to the ngEHT. So for us, I would say everything is signal to noise. Signal to noise. I don't know whether this is carried over by a legion, the Charlie Towns told Reinhard Getz, so that there is nothing like a diffraction limit. You only need signal to noise. Very much along the line which you depicted. So for ngEHT, what is the way to get to the sensitivity? Is it more telescopes or is it better receivers? Just projection from us, and we can't change the telescope pump we are given. So all of the progress is actually not by creating new, but by what you have and make them better. We need a flare for it. So this is why we see something different than you. I mean, for me, this is different. We need a flare.
I guess what I'm saying is that the people who do GRMHD, I'm just wondering, during a flare, there must be some panchromatic model that would account for the submillimeter that we will see, and the structures that we will see, and the infrared, unless.
And I mean, this is definitely an active area of work in the collaboration. There are many groups doing this. I mean, I showed some movies from Kaushik Chatterjee's work, but there's these, simulations now that are showing plasma information. Several groups have this when you go to high enough resolution, And it looks like these plasmoids are basically kind of the right site at the right place, doing the right thing for reconnection. But the problem is that we don't have the microphysics down in these simulations. So I think what will happen in the coming years is that as people move towards putting more kinetic, kick type approaches at these scales, which is becoming possible, we'll be able to get the physics we need to check the light curves, because right now we're limited in some ways by painting on, our distributions of particles in these simulations. But I'm pretty sure that this is going to be the right answer, these sort of flux tubes of these reconnection areas.
One physics where we could connect, because it distinguishes the large scale physics of the microphysics, is the magnetic field. So I could well imagine that if we have a flare and the vision is dominated by a smaller region, we're still in a similar part of the large scale magnetic field topology. So here is clearly something where I would see we could more easily connect actually our data. So we have the time of the ability which you can connect, but also the magnetic field or the polarization. So here this should also be easy then to have both things, to catch a flare in so many places is a hard one, I would say.
I just want to say one other quick little pitch, which is, of course, some of us have always been interested in whether there are jets, or not in the galactic center. And I think the hope would be, of course, that if these flares are lighting up the structure, if we can figure out they're going up, or maybe tracing the base of the jet in some way, that would, for me, be one of the more, that gets back to the question you had, Jose, but what's really exciting, I think there's a great potential to try to answer this question, maybe using the flares to sort of illuminate the space if it's happening.
Yeah, but I mean, for what it's worth, coming from the outside in, that little a figure that I showed, there is a successful coherent model now for the galactic center that explains the Fermi bubbles, the Rosetta bubbles, and can go not quite down to where gravity or EHT is going, but there is a model that, is predicated on some kind of time scale, like, black hole activity, 2.5 million years ago that lasted 10,000 years. And that probably gave rise to the bubble. So I think the challenge, as you point out, even when we have the multi-scale, multi-wavelength data, like knitting that all together consistently is going to be quite tricky. And from the simulation, and as Sera pointed out, Kaushik has also been doing these simulations where if you start out with a tilted disk or a misaligned disk, there are lots of transients that you see. So what remains to be seen with the question about the cadence, right? If these kinds of flares are, are they very rare? Are they very frequent transients? And that should tell us something again about the kinds of processes. Could be an indication of some kind of intrinsic misalignment. So I think there is much to be done even after observations are delivered, multi-wavelength and multi-scale, for us modelers to kind of knit that picture together. Especially, for example, I mean, I just mentioned the accretion rate, but the B field strength, and the just that, getting that to match on every scale, it's going to be a challenge, because I think, as Sera pointed out, I mean, there are probably microphysics we were missing, right? So with this sort of static painting on that we're doing for the sort of thermal state of the electrons.
Yeah, definitely having the target of opportunity capabilities of EHT plus ngEHT, I think it will be absolutely, a game changer, I think, for all these kind of studies, as Velana was commenting before. Andre, you wanted to comment?
Jim basically stole my question. I wanted to ask it, but you turn it into a statement, and every next sentence just deepens the same feeling. We need to get coordinated EHT, ngEHT, and gravity thing, because that's the way to understand what drives the flares and what we see in the Sag star with and without gravity flare. Whether there's more extended emission in the radio scale also during those flares which you detect, and then you can address. I guess you could be able to address much deeper the entire physics of this accretion process and events. Because if we just speculating now, it's model this, model that, but if you see that during the flare ngEHT or HT also sees some more extended radio emission, and you know what kind of spectral properties of that flare is, what mechanism. And finally, the question is, where are the protons in that disk, and where are they going? Are they going in your flares, or are they going in that? Well, they shouldn't certainly be in the photon rings, but what do they do afterwards, or when they not come into the photon ring?
Yeah, thanks a lot, Andre. Yes, I think this is indeed one of the key science enablers for the future. George, I think you also want to comment.
Yeah, thanks. So I want to return to this question about the microphysics. So of course we have all of these great stations that are prescribing these kappa models, variable kappa models, and so on and so on. But my impression from the plasma physics community is that there really is not a lot of consensus. A lot of simulations use very fanciful mass ratios for ions to electrons and so on. So there's a lot of uncertainty there. I'm wondering, has there been any discussion, or how could we get involved in discussion with the plasma physics community to try and use ngEHT observations, target them in some way to start answering these questions? What can we constrain actually about the particle distribution function? What would be most useful to constrain for those experiments?
Well, I mean, there are actually plasma physicists involved already, right? People like Bart Ripida is coming from that background, also Sasha Filipov and others. And I think there's quite a lot of interest at the moment in the flares and also in the gamma ray flare from M87, as well as from Sagittarius Star. And these communities are getting involved in using their first principle models. The problem is they're just really computationally expensive, so they're even worse than us. And in terms of trying to get anywhere. But I actually think, so I agree with you, that the constraints that could be really interesting will be these stochastic distributions, right? Because that's where we're off. We're off in the variability for Sagittarius Star. We're off in, probably a lot of other places. And my guess is that that's going to reveal where the missing physics is. And that's why we're also kind of excited about it.
Yeah, Jeff, I think you have also a comment.
Yeah, thanks. So I have a question that goes in a very different direction. We had a historical talk from Jim, and I'm curious to hear a little bit more about what people expected to find in those first couple decades of doing Sagittarius Star, VLBI. What was really driving that? And then, I think we've ended up somewhere maybe different from there. And so what does that tell us about what we should be expecting or planning for the future?
Well, of course, you go back almost as far as I do. But,
not quite, Jim.
I wasn't aware of a tremendous amount of forward thinking beyond just that raw desire to resolve the intrinsic structure. In other words, show the deviations from the lambda square curve. And of course, what got everybody really cranked up was Heino's simulations in 2001, which gave a real concrete sort of objective. I can't claim any deep thinking on that other than that. Since I have the microphone, I've been thinking up here about Frank's remark about signal to noise, the desire for more signal to noise. And it can be very important to us. We seem to be so thrilled, especially with having ALMA, that the signal to noise ratios are just astonishingly high. But in order to pick out the photon ring, n equals the lowest order photon ring, that's probably going to be difficult. And it's a fairly precisely known structure. So that's going to require raw signal to noise. And maybe that feeds into thinking about the size of antennas that you want for the ngEHT and how much money you want to put into really optimizing the LMT, which will presumably be the anchor station for observing outside the EHT schedule. So I have to wink over there at Michael. He gave me this idea during the coffee break.
Okay, we have two questions and then you, Michael.
Right, so my question is regarding spin measurements of Sagittarius A star. So 2009 to 2010 papers at anything from 0 to 0.6. The EST papers say it's anything from 0.6 to 0.94. So essentially we don't know what the spin is, right? So instead of treating spin as an independent observable, does it make sense to look for multivalent observables directly affected by the spin? So for example, if we know the spin of some black hole X, we by definition know some other multivalent observable as well, instead of the conventional way of having it the other way around.
Sadly, it's not so easily mappable. It's a much more complicated relationship. For example, if you take the accretion rate, the radiative efficiency, the spin, and where in the disk you are, all of that matters. So there isn't a simple way. People, who do the modeling have tried to see if there's any way to reduce the dimensionality, essentially, right, of this sort of complex surface of variables. So sadly, there's nothing that easy that one could do. And I think the, sort of inferring, so right now it's just from the library of images, GRMHT simulations, right? I think what one could try to do next, as I said, is the sort of bridging the scales. You would potentially have a similar library that goes further out, say out to the Bondi radius, and you would have to simultaneously match ngEHT data and stuff that you could get from multi-wavelength at larger radius. You'd have to simultaneously match with the library of the same spin. So that's one way of leveraging the scales to maybe say something about spin.
And I could just also maybe quickly add that there's another observable that was spoken about earlier this week, but I don't know if, not everyone was there, but I hope it will come back again, which is sort of the twistiness of the polarization. There's a lot of people working on this at the moment in the team, and this seems to be something that would be a really good distinguisher of spin, but that's yet to come.
Carson, is that you? Oh, yeah.
Can you hear me?
Yes.
Okay. So I think this is probably a question for Frank. So I actually joined the late this session, so I hope that this was not asked yet. So I actually spent some time on the imaging techniques for the EHT, and several years ago, actually when we started to work on imaging techniques for the EHT, I think it's fair to say all of us are all inspired by what has been done in the optical interferometric imaging. Because we actually share the same nature that in some sense actually the data are corrupted by atmosphere, and we use probably a very similar techniques so far. So I'm just wondering, so still actually we need to actually push our limit on the algorithm side for imaging in the next decade for the ngEHT, and I guess the gravity community, optical interferometer community, I guess also have some desire for the algorithm. So I just wondering is there any challenges or the scope for for the imaging techniques or whatever? I mean the software algorithm side. And do you see any cross section between ngEHT, Moran, and the optical interferometry community for such kind of development in the next generation imaging techniques?
Well, we are trying to learn from you in this particular case. I would say in gravity, we have done, I would say, the first years very basic things, de facto clean or model fitting, which is pretty straightforward in our case because the model is so simple, or the object is so simple, not the model, the object is so simple. Now, if you look at the images which I presented today, so we have already done the first step. So this is a code which now is a model-based imaging code which we are using, which is coming from a Garkin group. It's called NIFT, is the one information theory. But for me, as a simple-minded one, it's a model-fitting imaging. So we are learning to use your techniques. I think where we are still comparatively weak is in our ability to self-calibrate the data. I would say on a factor 2, we are still limited by systematics. So our deviations from the model are larger than the others, which we would estimate from the instrumental effects. And our ability or our techniques yet to take care of that, I think this is where you're far ahead of us and where we've not applied much thought yet to look beyond what you would call a closure quantity or something like that. But this is pretty simple still what we do here. There. And to get a feeling for the data one could get, I would say between the clean imagery and the one which I've seen here, we see roughly a factor 2, how we can go deeper, maybe a little bit more. But this is, and certainly there could be another factor of disorder just for the technique alone. That's true.
Michael?
Why don't you have closure phase?
No, we are using that, is what I'm saying, but we are this very simple ones still. I think the more difficult things, like if they are intrinsic. And because we measure baselines differently than you, we actually really interfere each pair of telescopes, and so there could be others which are related to antennas, or there could be was related to a particular baseline, which is not depending on antenna. And so on those things, we have followed some of what you've done, but certainly we have not covered all towards the end. Disability, I don't know how your raw data looks like in the end. I would say when you show your data, like in the talks, everyone sees a ring if you show your Fourier picture, but I don't know how much has been needed to come there. I think in our case, actually, we don't do much to our data at that level to come to the images. It's mostly data selection, I would say, a visual data selection, which for us makes the biggest difference, rather than a kind of a self-cry of in whatever form our self-calibration is on other devices.
Michael, please.
Yeah, comment on the question. The comment is on the photon ring. For the n=1 photon ring, if it was the only thing on the sky, we would detect it today with a signal to noise of 100. Right? For us, the whole game is decoupling that from the rest of the emission, and it's part of why this question of signal to noise, is that all you need? It's complicated, but we actually would have signal to noise to burn even for this very faint feature. I just find that kind of marvelous. The question is, I was really interested to get your take on the role of simulations in the ngEHT and this development over the next decade. And I was thinking simulations have played a huge role in inspiring observations, right? Simulations of the shadow, simulations of hotspots. These are a big deal for us, but I actually don't think that our major results on these types of projects in VLBI have relied on simulations for their primary interpretation, right? You don't need a simulation to interpret the shadow or the motion of features or superluminal motion or whatever. And so the question is, are we just going to quickly get beyond simulations can make contact with and their role is inspirational? Are our major results going to be tied to simulations? They're so expensive, as Sera mentioned. Should that be part of the project budget, right? Should we include that instead of requiring them to go off and get their own grants and just assuming it's going to happen? How should we approach the connection between simulations and observations in the next decade?
Yeah, I think there's going to be no escape from simulations anytime soon, and I think it would be prudent. So for the interpretation, I think much like has happened with the EHT collaboration, these various libraries of images, I think we're going to have a similar, we're going to need something similar. And the scope of that will become a little clearer once we are able to do this sort of bridging the scales with the current data for M87 and Sagittarius A*. If we can successfully knit these data sets together, then we will know the kinds of simulations we have to really be doing. At the moment, I think we're still debating, isn't that true, Angelo, about whether we need 3 zones or 4 zones, right? To capture the phenomenology. Like, do you need, so you need GRMHD, then you need just MHD. Then the question is, do we just need HD after that, or do we need, to break that region further in? Is there going to be a region where you don't have strong gravity, but gravity still matters? I don't know if Kaushik is here. He may be able to say a little bit, chime in here with the conversations that we've been having. So I think the kind of baseline simulation that we need, we are working on that now. And once we have that, and if we can successfully show that we can match multi-scale, multi-wavelength data, then we know the parent simulations that we'd have to do a suite. I think there's no escape given the complexity of these systems if we want to extract quantitative information.
So is it part of the observatory?
It has to be part of the observatory, very much part of, and it has to be budgeted in time-wise, effort-wise, and money-wise.
I mean, this is a huge discussion in the field right now, and it's like, because simulate, you just cannot do these calculations anymore with pen and paper, they're too nonlinear. And so simulations are here to stay, but then of course, like you say, people just sort of assume they appear for free. So when we write funding proposals, there's always this chicken egg, they're disjoint, and you have the instrumentation. I think there has been some cases, for instance, like LOFAR was a software telescope, where the software was considered a very important part of the observatory. And I think maybe we need to start thinking about a bigger view, but we have to also change the funding agencies' points of view on how to fund things like this.
Yeah, and so we have seen really an amazing, development in GRMHD simulations in the last 10 years. I remember doing my own simulations of, parcel scale physics, and it looked like, doing GRMHD and jet formation was something like, it would take like 20 more years. It was really only starting. And nowadays, I think one of the key aspects of simulation is to convert the microphysics with the micro and micro and microphysics. So the very small, so particle and cell simulations, I would tell you how magnetic fields developed and that kind of things, and the actual microphysics, that the things that we see with our telescopes. And in my opinion, this is also like decades away, but Sera, you may know better. I mean, do you think that, and Priya, do you think that this is something that we will see a significant improvement in numerical simulations from combining the completely very large different scales, and in time, by the time we will have the ngEHT?
Oh yeah, I think very much so. I think that I'm very optimistic, because these sort of peak simulations like particles and cells, combining the sort of state-of-the-art plasma physics with MHD, GRMHD, I think it's totally doable. The question is the computational time and the efficiency, and whether we will be able to explore a lot of scenarios to really understand, cause and effect. Because, you are limited by what you can put in. So you want to be able to put in a lot of different things to see. So I think computational time is going to be a key constraint, but I think it's doable for sure.
You want to comment? Okay.
But we are not running the risk that we create a virtual universe and we are starting to observe virtual physics while reality is different. Okay, now
No, we'll bracket reality, is all I can say.
Yeah, but we've seen that in other fields of astronomy also, where when things actually develop their own life, actually sets a full generation of new researchers in a direction. And at some point, okay, this is what we do in certainly the GHD is wait for that is to confront it with reality, to see what of that virtual of some universe is the real one. Can I ask a question? I didn't manage when Michi was giving a talk, but now I can't resist. So in these models which you have used to interpret your data, how does the Blanford paper from 4 weeks ago fit? The Blanford Phobos paper. Is there anyone in the audience who would like to comment? I know, or is it in well, that the energy is in the ergomagnetosphere than in the GRMHD, so to say, where this is covered.
Yeah, I mean, okay, I've heard Roger talk about this before. It's sort of his pet idea. It sort of reminds you more of sort of pulsar situations, and we know what happens in pulsars when they start to accrete. They don't function as pulsars anymore. They function more like black holes, producing jets and whatever, you know, what neutron stars do. So I mean, what I can say is, we know there's accretion. We measure that via the polarization. We know there are magnetic fields of a certain strengths, which are strong, but are not, excessive. I mean, these are 30 Gauss magnetic fields. And the GRMHD simulations are excessively good in describing almost all aspects. We are getting nervous because there is a factor 2 difference in the variability, even though we don't even have all the macros physics correct. So, I think if someone comes along and says, I can do it much better and have a new idea, it's fine, great. I mean, you need this, that's important. But you have a lot of work to do to convince the community that this is the much better answer than what we have right now, which is, by the way, sort of, 20 years of 30 years of research, first pen and paper and now fancy supercomputer simulations. So, of course, you should always listen to what Roger says. So in that sense, I think, it's important.
Alan, please.
Yeah, I want to switch topics a bit to a super resolution, which Jim brought up. Here, Jim. Jim looks like he's looking around for.
Alan is it?
Super resolution, it is something that I think a lot of people throw around, and there hasn't been really much done systematically about it. But one example of how I can get super resolution from say VLBA images is if I make a really nice image with all 10 antennas, and the beam has a certain size that's determined by the signal to noise to each of the antennas and so on, and the UV coverage. If I throw away the inner UV coverage, I'll get an image that has a smaller beam, but higher, but worse dynamic range, a lower dynamic range. So I can artificially get better signal to noise, and I think that they'll give me super resolution of the smallest structure at the expense of having more side lobes and stuff like that.
I think that's kind of a cheat. If you had your antennas, just in a circle, that's sort of an extreme case. Then the point spread function would be a J0.
Right.
And I think its beam width is 0.5 lambda over d. So that's a legitimate result, as you say, with lousy side lobe levels. But I think when you talk about super resolution, you've got to talk about a complete system for getting a high dynamic range in the whole image, not just.
Well, it depends on what you want. If you want high dynamic range, then that's another story. Then you want to even do natural weighting instead of uniform weighting, and so on. But if you want to ask what is a limit to how what your information is on the smallest scales, that comes from the longest baselines.
Mm-hmm.
And to say that you're cheating by only by considering the resolution you get with the longest baselines, I don't think it's really quite correct. There's a lot of information. What the problem is that there's a degeneracy between different models. For example, a double source model, if it's only partially resolved, the double source model can give you the same visibility as a single source model that has a size about equal to the size of the separation of the double. And so there's a degeneracy there that you lose when you try to do super resolution. But that occurs somewhere better than the 1.22 lambda over d.
Talking about throwing away data, the experiment I would like somebody to do, maybe it's been done with, for example, a large array like the VLA, is to throw away the outer half. Try all your super resolution tricks on the inner half and then compare it with what you get with a full array. And to see whether if you come up with any surprises in the half size array that are actually borne out in the full array, which is sort of like the truth data.
I see the ship wants to say something about.
Yeah, I think they up there. I cannot see you.
Sure. Sorry, I can go first. Hi, it's Daniel. So speaking of super resolution, I've also been thinking about Andrei Lovanov's 2005 work on template discrimination. Is the world ready for the ngEHT to be a template discriminating or a template fitting instrument? When we go to these very distant sources or very dim sources where we want to make these aggressive mass and spin measurements, these are intensely model dependent. If you want to be able to do anything sensible or resolve or really super resolve a ring, are we at the point where we see two black holes, they both look kind of like prograde MADs? Can we just make that assumption, publish fits to marginally resolved sources, and is the community ready for that? Which I guess is a question both of super resolving and community trust in these MAD models, and also one of community eagerness for people working in more on the galactic side. Are they willing to accept something that's intensely model dependent?
I mean, they have for LIGO, right? I just see why not. I think it's just that the kinds of templates and template libraries we'll be talking about for ngEHT will be significantly more complex. But I think, responding to the question that Michael had, I think that is the direction in which we probably have to go. And I think LIGO observations are not disputed. I mean, there's now, after about several hundreds of events, there's been questions about how restrictive are our templates? Are we missing interesting physics that is not captured in the template, right? So I think I would say the community would be willing to believe us.
Well, yeah. So I think there's a middle ground here where you don't know what you're after. So imagine the EHT when we didn't know there was a ring. Right? We were guided by simulations, but we were very, very careful with our priors, right? We did not want to over prior the imaging process because that really would have been death. Right? Thankfully, we had these nulls in Fourier spacing, which was pretty clear. But now let's think about the n=1 ring that Michael was talking about. We have reason to believe that photons do orbit around this black hole, right? But we also have reason to believe that the n=1 ring should be pretty achromatic, right? So if you go to 345 and 230, that's a very powerful discriminant, right? There should be a feature, a strong feature that's about 10% of the total flux density that has the exact same structure at 230 and 345. Then you should have all the gastrophysics around, which will have a spectral evolution. And that we can fit. So you can think about doing like a hybrid approach that like Avery and others are pioneering, where you fit a feature that you know should be there, that has to be the same in both these frequencies, and then you do the imaging later with like a multi-wavelength process like Andrew Shale has been developing with others. And that, I don't think that's cheating, right? Because gravitational lensing is supposed to be achromatic, right? We know something about the plasma as it evolves from 230 to 345. So I think there's a middle ground where we use what we know, and we can effectively get super resolution. We actually can't see the n equals 1 ring, but we can model it and subtract it out and then do the imaging from there. I think maybe that's believable, Daniel. Maybe people are going to bow down before that God. I don't know.
Ivan also wanted to
No,
participate.
it was just a quick comment on what Alan was telling about this super resolution and long baselines. So you need the whole UV coverage, Alan, to have the super resolution. It's not. I'm here, Alan. So it's not enough with the long baselines. You need the short baselines. Yeah, here.
Alan, right there.
So you need the whole thing. You need short baselines in order to be compared to the long baseline, so that you can check whether you are resolving the source or not. So you need the whole data set. It's not enough with the long baselines. So it's a bit subtle. Yep. Yeah, but if you want to model fit and resolve that source, you need as much UV coverage as possible, not only the long baselines. So you still need that, and you still need to have the high dynamic range in order to be able to super resolve. Otherwise, you are lost.
Yeah, but what we do is if we have all the baseline, then what we say is that the beam is this fairly broad structure.
So basically, it depends on how many short baselines you have in units of how many long baselines you have. So how is the baseline length distributed in your UV coverage? That's another matter, but you still need the short ones.
But then essentially you're throwing away the information that you have on the longest baselines.
May I just interject?
I think we are getting a little bit too.
Not valid.
I think it's maybe too technical for a discussion.
Yeah. So perhaps Andre, if you want to have a quick comment, it's about this or something else.
Right. This is exactly the type. It's just what Dan was just starting. If you fit templates, you of course depend on the SNR of your detection and nothing else. If you use imaging, free mode, you depend on your instrument performance. Hence, you need the entire UV coverage, and you depend on the knowledge of your gains, and you depend on the accuracy of the convolution. So you can call all these terms in terms of SNR of each of those processes: SNR of detection, SNR of knowledge of your gains, and how reliably you recover the structure. So SNR of that deconvolution process, and the minimum of those 3 SNRs, roughly speaking, gives you the amount of super resolution which you allow yourself. So basically, you divide your formal PSF by square root of that SNR, and that's the mathematical limit how much you can super resolve. And many other domains of physics and optics, they call it outer band of extrapolation, and they also analyze how much you can extrapolate out of band. We have a much better situation because we work with deconvolution firsthand, basically from the data. In many other instruments, it's not possible. You have to do it with additional tricks. And that's why in difframetry and also for the gravity measurements, it provides an additional handle on resolving the structure. And I think we should use it fully with the ngEHT. With EHT in RML methods, they actually show that, exactly that. What you see as super resolution in RML, it's exactly that. It's your knowledge of your data, knowledge of the instruments, and the accuracy of the convolution. The minimum accuracy of these 3 factors determines how much better you see beyond the formal PSF.
Peter?
I just want to come back to the point that Daniel raised, which I think is really important, is that a given state of the array, and not just in astronomy, but in particle physics, there's always a trade-off between being open to new things and finding out unexpected things from the outside, and using models or triggers and data cuts to test things that we think might be there, and we want to know how they'll come, whether they're there. If you want to find something at the LHC, you need an elaborate set of triggers and data cuts to pick it out of all the and to the 15 events that are happening. And if we want to pick out something that's beyond the visualization capabilities using a template at a given state, we should do that. And then as the array expands, new things will become visible and possible, and new opportunities to see unexpected things. But we're going to have to be flexible in figuring out at a given technological state what we can probe using model-specific or template tests of what we think is there, and the sort of complementary goal of being open to surprises and the unexpected. And both are part of what we're going to be doing, just as both are part of what you have done in particle physics for generations. So I think these things are compatible, but often complementary.
Okay, so I think we are reaching the hour. It looks like we are in a black hole here in Granada because time really, seems to be going slower. So I would like to first to thank all the invited speakers. So thank you very much, Priya, Sera, Frank, and Jim. So thank you. And also now we are reaching to the end of the ngEHT meeting. So I would like to thank project scientist Jeff Bauer for helping in organizing all this and all the wisdom from the management team. It's been really a pleasure to host an honor and a pleasure to host the ngEHT meeting here in Granada. And I think I speak for everybody in the LOC. And I like to have all the LOC here, please. And they have been doing an amazing job. And so we have Antonio, we have Teresa, Valia, Mariana, Rohan, Ilje, Rocco, Juan Yao, and we are missing Pablo. We are missing Pablo. Thank you very much. Thank you to all of them. Okay, and then with this we conclude the ngEHT part of the meeting, and we very much look forward for continuing with the ngEHT tomorrow. We had amazing the next 3 days to discuss ngEHT science and array design. So see you tomorrow. Thanks.
Could we please have a round of applause for José Gómez?